We're going over homework unit 10-2, and in this particular situation, the lesson was a bunch of tables, a bunch of equations that we went from there to tables to graphs as we investigated how an absolute value graph compared to a linear graph, and then we looked at those parameter changes. What we want to do now is on the homework is we're just going to investigate going from a table of values to an equation. And so I'm just going to do the entire homework session, page 266, just as a final brush up on this. Remember that with a table, we really don't know what we're dealing with. And so we're going to start with change in y, change in x, to determine whether it's linear, quadratic, or exponential. And what we're using is the regression rules from the first of the book. And we'll be reminded of those as we go. The first change in y, a gain of 4. Its change in x is a gain of 1, so we have a 4 over 1. The next change in y is a gain of 4. Its change in x is a gain of 1, so we have a second 4 over 1. The next change in y is a gain of 4. Its change in x is a gain of 1, so we have a 4 over 1. The next change in y is a gain of 4. Its change in x is a gain of 1, so we have a 4 over 1. We have a constant change in y, change in x. So that means that it is linear. And if it's linear, then that change in y, change in x is the slope. And along with the slope, for linear, we need the y-intercept. And the y-intercept is y when x equals 0, or the point where the line crosses the y-axis. And I obviously missed there. And so my y-intercept is 3. So my equation would be y equals slope 4 times x plus y-intercept 3. Any questions on that? Okay, number 2. Number 2, again, at the beginning, we have no idea what it is. We're not real sure how much space it's going to take up. And so we're going to just kind of clear things out so we have all the space that we need. We're going to begin with change in y, change in x, and determine what it is. The first change in y is a loss of 3. Its change in x is a gain of 1, so we have a negative 3 over 1. The next change in y is a loss of 3. Its change in x is a gain of 1, so we have a negative 3 over 1. So far, it's looking linear, but all of a sudden, things turn around on us. We have a gain of 3 rather than a loss of 3. Same number, but it changed signs. And then we have another gain of 3, gain of 1. And so we had a negative 3, negative 3, positive 3, positive 3. And that's what makes us think of an absolute value graph. Because what was looking linear turned, the slope changed all of a sudden. And so what we're going to have is y equals something times absolute value x plus something. And remember our little trick to make what we know about it so far look like a big O X, and then we're going to find the M and B as if it was linear. And to do that, we're going to take some points, some O. If we're going to deal with linear, we really only need 2. So we're going to take the old x of negative 2 and negative 1, the first 2 up there, and we're going to plug value x and get a new x. So absolute value, negative 2 is 2. Absolute value, negative 1 is 1. And so we have new x's. And we're going to put those new x's with the old y's that went with them, which was 11 and 8. and we have a linear situation. So then we find change in y, which is a gain of 3, change in x, which is a gain of 1. So the change in y over change in x is a 3 over 1. That means that there's a 3 in that position. And then we're going to pick a point like 211 from our new table and the slope from our new table. And we're going to get the supposed y-intercept out there at the end. We're going to take the y in place of y, slope in place of slope, x in place of x, and solve for b, which is in the y-intercept position. And so we have 11 is equal to 6 plus b. Subtract 6, and we get b is equal to 5. And so that goes in the b position. So that tells me that my equation is y equal 3 absolute value x plus 5. Now let's see if it works. Plug in a negative 2. Absolute value negative 2 is positive 2 times 3 is 6 plus 5 is 11. That worked. Let's just try another one. We'll plug in this 2 over here. Absolute value of 2 is 2 times 3 is 6 plus 5 is 11. Let's try the 1. Absolute value of 1 is 1 times 3 is 3 plus 5 is 8. So you can see that we actually did get the right equation. And we figured all that out without a calculator. We did it all on paper. Kind of cool, huh? Number 3. We have no idea what it is. And so we're going to begin with the change in y, change in x to try to figure out what it is. So the first change in y is a loss of 6. Its change in x is a gain of 1. So we have a negative 6 over 1. The next change in y is a loss of 2. The change in x is a gain of 1. So we have a loss of 2 over 1. The next change in y is a gain of 2. Its change in x is a gain of 1. So we have a 2 over 1. The next change in y is a gain of 6. Change in x is a gain of 1, so we have a 6 over 1. Now that is not an absolute value, because absolute value would need to be negative 6, negative 6, negative 6, positive 6, positive 6, positive 6. You can't have 6's and 2's. So it's not linear because it's not a constant change in y, change in x. It's not absolute value because the numbers changed on us. But it is the change in y that's changing, so we need to look for a pattern of change in the change in y and apply those regression rules at the front of the book. If we look for a pattern in the change in y, you can see that negative 6 plus 4 is negative 2, plus 4 is 2, plus 4 is 6. So the pattern of change in the change in y was a plus, 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 so it tells me that this is quadratic. Now we could go to the calculator and do a quadratic regression, or we could think, well, maybe it's a something times x squared plus something, and it's not a big fancy quadratic like y equal 3x squared plus 6x plus 7. Maybe it's a quadratic with a missing b term. If it is, we can regress it with our same trick. If our little trick falls apart on us, then we'll have to try something else. So let's just try. We're going to make that our new x. And so we're going to look at some old table points. The first 2 points were negative 2 and negative 1. So far we had x squared, so we would plug those in. Negative 2 quantity squared is 4. Negative 1 quantity squared is 1. And so we got some new x's. We're going to put those with the y's that went with those original x's, 9 and 3. We're going to do change in y, loss of 6, change in x, loss of 3, negative 6 over negative 3, which is a negative 2 over 1, goes in the slope position. And then we pick a point from our new table. The first one is 4, 9. And the slope from our new table, 2. We plug those into y equal mx plus b and solve for the b. So we're going to take the y in place of y9, slope in place of slope 2, x in place of x4 plus b. Multiply, we get 9 is equal to 8 plus b. Undo addition by subtraction, b is equal to 1. That goes in the b position. So it appears that our answer is y equal to 2x squared plus 1. But we should verify by plugging in some points. So let's plug in the negative 2. Negative 2 squared is 4 times 2 is 8 plus 1 is 9. So that one checks out. Let's try another one. Let's plug in the negative 1. Negative 1 squared is 1 times 2 is 2 plus 1 is 3. That one worked out. Let's try this one. 1 squared is 1 times 2 is 2 plus 1 is 3. That one worked out. And so you can see that we indeed came up with the right equation. All on paper again. Now, if there was a bx term, then it would be a little more complex to regress it. You could still regress it on paper, but it gets kind of crazy. So I won't go into that. There's a way that you can do this on paper that takes about a sheet of paper. And I've got a way that I invented that takes about half sheet of paper, but it's still complex. Okay, number 4. Number 4, we have no idea what it is to start with. Again, on any of these, and I haven't done this, you could graph and get a visual of what it is, and then you would know if it's linear, quadratic, or exponential. But then you just use the calculator. If we're going to do it on paper, we got to do the change in y, change in x anyway. So we just as well start with that. So change in y over change in x. Let me start over because that didn't come out like I said it. Change in y over change in x. The first change in y is a gain of 1. Change in x is a gain of 1. And so we get a 1 over 1. The next change in y is a gain of 2. Its change in x is a gain of 1. And so we have a 2 over 1. Next change in y is a gain of 4. Its change in x is a gain of 1. So we have a 4 over 1. The next change in y is a gain of 8. Its change in x is a gain of 1, and so we have an 8 over 1. It's not linear because there's not a constant change in y, change in x. It's not absolute value because it doesn't go like something like negative 3, negative 3, negative 3, negative 3, positive 3, positive 3, positive 3, positive 3. But we have identified that the change in y's are changing, so we're going to look for the pattern of change in the change in y and think about our regression rules. The pattern of change in the change in y numbers is a times 2. 1 times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. If the pattern of change in the change in y is a times times times, then it's exponential. If that times is a times 2, then it's a base of 2. And so we're going to have y equals something times 2 to the x plus something. We're still using our trick. We're going to call this a big O X, and we're going to look for what's in the M and B position. So we're going to take our old x values. We just need 2 points to get aligned. So we're going to take the first 2, negative 2, negative 1, and we're going to plug them into what we have so far, 2 to the x. So we plug them in. 2 to the negative 2 would mean the reciprocal of 2 squared. The reciprocal of 2 squared is 1/4. We plug in a -1, we would have 2 to the -1, which is the reciprocal of 2, which is 1/2. So there's my new x's. I'm going to put those with the y's that went with those x's, -2, -1. And then I'm going to do the change in y, change in x. The first change in y is a gain of 1. The change in x is a gain of 1/4. And so we have a 1/1/4 divided by 1/4 is the same, dividing by a fourth is the same as multiplying by its reciprocal 4. And so we get a 4, and that 4 goes in the M position. And so then we're going to pick a point from our new table, like 1/4 -2. And I'm running out of space, so I'm going to do it over here. And the slope from our new table, which was that 4, and we're going to plug them into y equal mx plus b, and we're going to solve for b. So we're going to put the y in place of y -2. I'm going to have to erase this new table out. We've got all we needed out of it already. Slope in place of slope 4. X in place of x 1/4 plus b. We're going to multiply. -2 is equal to 1 plus b. A fourth of 4 is 1. Subtract 1. B is equal to -3. And so that -3 goes in the position. So my equation is y equal 4 times 2 to the x minus 3. You can see if it works. We'll just plug in the 2. 2 to the second is 4 times 4 is 16 minus 3 is 13. That one worked. Plug in a 1. 2 to the first is 2 times 4 is 8 minus 3 is 5. That one worked. And so you can see that we did get a good equation. Interesting. We're regressing all kinds of equations 100% on paper with no use of the graphing calculator. Okay? Now you realize that these can get complex, and they're going to get complex if they look like this. Whoops, that wasn't what was supposed to happen. That was kind of weird, huh? There we are back again. If you have something like this, y equal 3 times open x minus 4 quantity squared plus 6. When you get something in there with the x, whether it's a quadratic or whether it's an absolute value or whether it's square root, because that's in there, we can't use our little mx plus b trick, okay? And so, because we'd have a hard time knowing that that was in there, so that then we got to get these real complicated regression deals. So if you start working and you get it and you plug and check and it doesn't work, then you know, well, it's a complex one. I really need to go to the graphing calculator and get it, or you have to learn some fancier formulas to get it done. So, but that'll work with some, and we can do it, test it, and hopefully find a lot of equations we couldn't in the past. Number 5 and 6 I threw in here. This takes us back to page 96, example 7 and 8. Page 97, rule 5 and 6. We learned that if there's a constant y, then it's a horizontal line, and the equation is y equal constant y. We learned that if it's a constant x, then it's a vertical line, and the equation is x equal to constant x. Remember that on a vertical line, the slope is undefined and there's not a y-intercept. On a horizontal line, the slope is 0, and the y-intercept is that constant y3. Any questions on page 66 homework? We just did